Welcome to the 1-hour narrated course brought to you by Structural Insulated Panel Association. This course is titled Residential Design with Structural Insulated Panels and is approved for AIA Continuing Education credits. My name is Al Cobb, and I've been in the SIP industry, or the Structural Insulated Panel industry, for well over 26 years. I am a past president of the association, and I have worked both in manufacturing, distribution, design, engineering, as well as installation, and most recently in training and consulting. I run the SIPS school located in West Virginia outside of Washington, D.C., and I provide training and consulting to individuals all over the world looking for information about structural insulated panels. And over the next 1 hour, I will provide some input as to how panels can best be utilized in your designs as you move into the world of structural insulated panels. This is the standard boilerplate information provided to you by the American Institute of Architects. It's the approved promotional statements. I'll give you a second to read these. This course is in a standard format, not as a live instructor, but as a narrated course. Obviously, I'm not standing in front of you, I'm in your computer. The course is for 1 credit hour. It's for health, safety, and welfare, and you will have the ability to receive certificates for the course, for course attendance, or following along with me on this 1-hour course. The course description is basically an outline of SIPs, how they're used, what is a SIP, and how a designer can gain a better understanding of the utilization of SIPs, some of the detailing that goes into it, how they are used in assemblies, and how we use SIPs to provide optimal energy efficiency. And of course, we'll talk about durability. One of the factors in SIPs that's very important when we make a very tight envelope. We also want to look at the building science and the durability aspects of a structural insulated panel envelope. We'll walk through a couple of case studies. We'll look at some design strategies, and along the way we'll throw some words of wisdom your way to hopefully make you a better architect or a designer as it relates to SIPs. At the completion of this course, we would like to think that you will be able to describe and define what a structural insulated panel is and how it can be used in residential applications, understand the energy efficiency aspects, the strategies that are used in order to get maximum efficiency when using a SIP, also be able to illustrate and understand the design and engineering methods used to work with the overall design methods of building with SIPs, and of course list some of the current industry assembly standards. The course outline is as follows. Roughly, we're going to talk about the basics of SIPs, what a SIP really is and what makes up a structural insulated panel. We'll go through some various applications. We're going to talk quite a bit about the energy efficiency and the green building aspect of a SIP. Then we'll break out into designing with SIPs and the engineering of SIPs and some of the tools that we use to better help understand the engineering of working with SIPs through a design. We'll talk about SIP manufacturing, and then we'll go into SIP construction as well. So what is a SIP? Well, we hear that a lot. What exactly is a structural insulated panel? It's pretty simple. It's a composite structure. It's made up of basically 3 elements. It's going to be a foam core. The foam core in the industry, in North America, is predominantly expanded polystyrene, or known as EPS. Some people refer to it as the white board, even also known as bead board. It comes in a variety of densities, but EPS is the standard. Next is XPS, or extruded polystyrene, most often known as styrofoam. It's typically colored. It could be a green, pink, or blue foam. Has a slightly higher density in terms of its core foam density. And lastly, it could be made up of polyurethane. That's the core. If we look at the structural facing, you will find that predominantly, as in 99% of the structural insulated panels manufactured in North America, use a 7/16 exposure 1 rated oriented strand board. These could be used in panels as small as 4x8 or all the way up to what we might call a jumbo panel, wherein the panel could be 8 feet by 24 feet long. In all cases, these components are adhered together I should say not in all cases, because in the polyurethane's case, the polyurethane is the adhesive, and when it expands between the skins, it creates its own structural bond. But in the case of EPS or XPS, the structural adhesive is no different than the engineered adhesives that are used in many other engineered wood components, be it LVL, I-joist, Paralam, Glulam. The same type of adhesives are used to bond the foam core to the 7/16 OSB skin, which make up this composite structure that is capable of carrying a great deal of load. So now that you understand basically what a SIP is, where did they come from? Well, originally they were developed back in the laboratories of Madison, Wisconsin. The Forest Products Laboratory was the one that first developed these back in the 1930s, and they referred to them as stress skin panels. The reason they were doing it was looking at the use of our nation's most abundant natural resource, which was wood, and the concern was, well, gee, we're going to use a lot of wood, and is there a better methodology that allows a improved efficiency when using wood? And they came up, of course, with things like sheathing, plywood sheathing, and then now, of course, the oriented strand board. And that material, when utilized in a stress skin panel, as it was referred to back then, could be laminated, and it was shown or proven to show great amounts of strength in carrying loads. Today, the foam cores, which were introduced in the late 60s, now make up the modern structural insulated panel as we know it today. So this is what we have when we look at the SIPs of today. We have the rigid foam core. We have a 7/16 OSB skin. Now let's not say it's always going to be 7/16. We can vary from that. You can go to a greater thickness and achieve even greater structural load carrying capabilities. Then you have the structural adhesive. The structural adhesive bonds the core to the skin of the panel and makes it one solid composite panel. And lastly, we have optional electrical chases. These chases are included in the core of the panel by many of the manufacturers, and they do this to allow a much quicker and simpler methodology when it comes to rough-in wiring of the SIPs. The standard structural insulated panel does in fact use oriented strand board, but that doesn't mean it's the only panel out there. You have other options. One that is found quite frequently is a metal skin panel. Predominantly the metal skin panel is used in the refrigeration industry. It is not one that is predominantly used for carrying gravity loads. It's typically a cladding that is attached to some type of a steel structure. It's much more commonly used in commercial structures. It's very common in Europe. In the US, predominantly the only place you'll see it is in warehouses, refrigerator warehouses, or refrigerated freezer commercial spaces. Other types of skins include cementitious skins. In this case, we have a cement skin laminated to either side. The skin has both pros and cons. Pros, of course, is that it is not wood, in that it does not have any moisture concerns whatsoever, or perhaps termite concerns. Also, those attributes could be defined towards metal skins as well. But the disadvantages are, one, it doesn't have nearly as much code or testing approval. It's very heavy, as well as it's more difficult to fabricate and work with in the field. Also, the largest skin that you can get is going to be, or that's provided in the market today, typically is going to be only up to about 4 by 10 feet. So it knocks you out of the ability to design using the jumbo panels, or the panels that take up a lot of, cover a lot of area very quickly, which is one of the things in speed of installation we enjoy when using the jumbo panels. When we look at SIPs, we are looking at a foam core panel that's laminated. We are not referring to a SIP as one that is prefabricated or has a stud wall that has been pre-insulated. That's not a SIP. SIPs do, however, replace traditional stud walls. They are structural by nature, so therefore there are no studs. Think of it as nothing but a foam core panel that's carrying all your gravity loads around the entirety, typically, of the exterior envelope. They provide a much higher R value, and they are substantially stronger than traditionally stick-built walls. The idea in using OSB as the load-bearing element, not necessarily load-carrying, but load-bearing, the equivalent of a 2 by 10 stud wall, 16-inch on center. Let's talk about some SIP details. This is a critical moment because we need to fully understand that as a designer you have a number of options when it comes to in-plane joint configurations or in-plane joint details. The one you're looking at is known as the surface spline connection. It uses typically 7/16 OSB ripped into small splines that fit half into one panel, half into the other, and this allows the vast majority of the foam core to come in contact and be sealed by some sealant specified by the manufacturer, which helps maintain airtight integrity. Now what we have is an assembly, whether it be wall or roof, where the foam core is not interrupted. Therefore, we have minimal thermal bridging. When using this type of detail, the panel is doing all the work. It is handling all the transverse loads without the benefit of any lumber being used at the spline. Once the panels come together in the field, they are sealed, whether it be some type of a mastic or a foam, which we'll talk about a little bit later, and then perhaps in addition SIP tape may be applied to the warm side of the assembly as code requires or as climatic conditions require as well. This detail is very similar to the previous one, which was the surface spline, but in this case it's referred to as the block spline. If we think about that little section that is right at the joint of the panel, and instead of providing two separate 7/16 OSB splines, but instead we take those two splines and we laminate them to a little block of foam and we create what might be referred to as a mini SIP. That SIP, also known as a block spline or in some cases a super spline, slides into the edge of each panel, and when it comes together and is sealed, you have in essence the exact same configuration of strength and thermal performance that you would see in the surface spline. The reasons one might use one over the other is strictly a case of manufacturing processes. The manufacturers may have equipment that better allows them to use block splines, or they may have routing tools that better allow them to efficiently create panel edge treatment that receives single or double surface splines. It's just a manufacturing situation. That's not the important point. The important point is that this detail or this type of joint allows the panel to do all the work, and it minimizes the thermal bridging within the panel. On this detail, you'll see that the foam from the panel on the left and the foam on the panel on the right do not come together. Instead, we are dealing with a thermal bridge. Now, that thermal bridge is double-dimensional lumber. The advantage of this double-dimensional lumber is that it increases the span capacity of a panel for a given thickness. If we have a span condition where we need to increase its load carrying capacity, we have two options. We can go with a thicker panel because thicker panels span greater distances, or we can change the joint configuration. The joint configuration can be made such that it has lumber in it, and that lumber adds to the span capacity of that panel. After this lumber goes together, you still have to seal it. You can very quickly see that the joint in the panels and the joint in the lumber actually line up. So we are relying on that continuous sealant right at that joint to maintain its airtight boundary. This is also where we might employ SIP tape, a tape that basically ensures an airtight boundary or an air boundary on the warm side of the structure acting as a vapor barrier. In this plan view detail, we have two panels coming together at a corner, 90-degree corner. One panel is the long, one is the short. This is a standard lapped connection, and the panels are brought together and fixed or fastened with a typical panel screw. That panel screw might be at 24 inches on center as it comes up the wall corner. And those screws penetrate through the long panel, or the top panel in this diagram, and into the lumber that is in the edge of the lower panel. The joint that is critical in terms of air sealing, of course, is the interface between the two panels, where sealant needs to be applied continuously so that we don't get any air coming through that corner joint. As a designer, of course, you want to put windows and doors into the wall assembly. When using structural insulated panels, this is not only easy to do, in some cases it's really fun to do, because we don't need to always require, or we don't always need to install separate structural headers. The panels are structural and therefore they can act in some cases as their own header. If we don't have a point load, the windows or doors are not too wide or too close to the top of the panel, this allows us to do exactly what you see in the photo, which is to put single dimensional lumber around the perimeter of the opening. This is done by recessing the foam 1.5 inches. That foam relief then allows the dimensional lumber to be sealed in place between the skins and nailed off on both sides. Fastening is typically done with standard nails or staples on 6 inches on center. Moving on with more SIP details, here we have a section view of foundation wall, which is sharing or carrying the load of both a floor system as well as a wall system. It should be no surprise that when we pulled our floor system inside the insulating envelope, we improve the energy efficiency of our structures immensely. It's because floor systems leak. All floor systems leak, and when they come all the way to the exterior of the wall, or the exterior of the assembly, the structure, air leaks through floor systems. So by pulling this floor system back and allowing the SIP to come all the way down, we gain the advantage of much higher degree of air tightness. This next detail showing a floor system is very typical as a hanging floor system or a hung floor system between a first and a second floor. In this case, a top mount floor hanger goes over top of the first floor wall. The floor joists stay inside of the insulating envelope. The 3/4 inch T&G floor sheathing goes over top of both the floor joist and the first floor wall panels. We increase our diaphragm strength tremendously by doing this, and then we stack the second floor wall panels directly on top of that. All of the red marks on the detailed drawings are indications of sealant to maintain airtight integrity. Here's the detail of the connection between roof and wall. In this case, the wall panel has been fabricated to the angle which matches the roof pitch. The double dimensional lumber has been beveled both sides. It's a double beveled lumber which slips into the top of the wall panel. Sealant is applied to the top of that wall panel before the roof panel drops into place, and then again you see a panel screw that extends through the roof panel and penetrates fully into the dimensional lumber that is the top plate of the wall panel below. If we look at the apex of the roof, or the ridge of the roof, this is where the two roof panels come together. You can see the SIP screws penetrating through those panels and into what is being shown as the ridge beam. The support for the SIP roof still needs to be taken into consideration, and in this case it is a solid ridge beam. You'll notice the joint between the left and the right panels shown on the screen allow for sealant to be injected into that joint to provide continuous or a complete air sealing methodology such that we don't have any air leaking through our ridge. That's a very critical joint to be sealed properly. You'll also notice that SIP tape at the ridge, it says required. This could be required either on the exterior or the interior, never both, because we never want to seal moisture into an assembly. We always want to allow it to dry. SIP assemblies, as much as any energy efficient assemblies, need to dry, and therefore you should never forget that the drying of the assembly is very, very important, and this is critical always at the ridge connection. In many structures, you might find yourself very comfortable with using SIPs on the walls, but not on the roof, or for some reason it might not work in a roof application. And that's quite all right. Using a SIP for walls and conventional trusses for the roof is commonly done. And this detail shows very clearly that the top of the wall panel has a top plate, shown as a 2x top plate. On top of that, you'll see there's a 2x ripped cap plate. This is sometimes referred to as a shim plate. The reason we do that is the ripped shim plate or cap plate provides full bearing for the truss to sit on top of the panel, and this actually increases our load carrying capacity of the wall panel below. In this case, you'll see we've got a 1 foot heel height that we're dealing with in the truss design in order to give us a full height of insulation that is going to go into that upper truss area to provide insulation much like you'd see on any conventional insulated truss package. I've spoken about SIP screws on a number of occasions. These screws come in lengths anywhere from 6 inches all the way up to 16 inches long. They are used to fasten the panels either to a frame, fasten to themselves, or fasten to ridge beams or other structural members. The points on these screws can be for a thread point into wood. They can be a self-tapping light-duty penetrating screw, or in some cases the heavy-duty point, which will penetrate into up to 3/16 mild steel. So if you're on a metal building and your roof panel needs to be attached to that, this heavy-duty drill point screw will allow you to do that. The screws are 1/4-inch shank steel. They're tempered steel. They have a pan head that allows it to pull in tight and be flush with the outside of the OSB skin, so it doesn't transmit through any siding, shingles, or anything of that nature. In addition, I've also spoken about in SIP details the need for sealing. Sealing is absolutely critical. We want to make our buildings airtight. Buildings need to be airtight in order to be energy efficient. It is absolutely completely misunderstood when somebody says buildings can't be too tight, they have to breathe. That is incorrect. Buildings should be exceedingly tight, and then they should be designed to be able to dry. Buildings don't breathe, they dry. And moisture control in energy efficient buildings is incredibly important. In order to make them airtight, which we want to do, we use a combination of either expanding foams, mastics. Other types of sealants include gaskets or sill seal. In this picture you'll see 2-part foam, which is in the upper right hand corner, where we're using a polyol and an ISO, which together combine to create polyurethane. The single component foams down below are gun applied. These are used in anywhere you can possibly think of that air might leak through the assembly, around chimney stacks, around plumbing stacks, windows, doors, joints, you name it. If air can get through, injecting foam into the joint is a great way to improve energy efficiency of the system. There's a lot of misinformation out there about energy performance and how panels truly perform, especially when one only looks at a rated R value. The rated R value only tells half the story. The other half of the story is air tightness. So Oak Ridge National Labs, in conjunction with the Structural Insulated Panel Association, did some tests. And in these tests, what they did was looking at whole wall R values of panels as it compared to conventionally framed systems. And one big part of this test had to do with the thermal bridging that is inherent in conventionally framed systems. When we have a 2x4 or a 2x6 stud wall where the studs are spaced 16 or 24 inches on center, we have a framing factor, or in other words, a thermal bridge factor, that means that upwards of 20 to 25% of the wall might be solid lumber. In a SIP wall, the whole wall R value is substantially better or performs better. So even though you might have a rating of R14, a comparable 2x6 stud wall that has an R19 rating with fiberglass in it doesn't perform that way. That's why there's a great deal of misunderstanding about what the true R value is when we compare SIPs to conventionally framed wall assemblies. I talked a lot about thermal bridging, and of course when we look at thermography or thermal imaging coming out of a thermal camera, you can very clearly see what a thermal bridge looks like. It's the dark lines on the left in conventional wood framing. If we look at the SIP on the right, you'll see that homogeneous SIP core, especially when uninterrupted by maintaining a design that allows us to use the surface spline, we get continuous foam throughout the entire wall or roof assembly, and when we take a picture of it, this is what it's going to look like when we look at the picture on the right, and that's a good thing. If we want to get super geeky about looking at the statistics of thermal bridging, we could put some of our analysis through a Wolfe analysis or something that might look at the transfer of heat through the assembly, and you can see above, just as I pointed out at the beginning of this presentation, the surface spline does not allow for those huge variations in the flow of energy from interior to exterior skin like it does where thermal bridging occurs at studs, as you see at the bottom of the detail. Characteristics of SIPs. I've talked a lot about air tightness, and it's because I truly enjoy seeing houses perform very, very well, and they do that by virtue of the fact that they are airtight. houses need to be airtight, and SIP houses can be made very, very airtight when tested with a HERS rater or a home energy rater using the simple blower door test. This blower door test can be used not just to verify how tight the house is, but just as importantly, to look at the quality control of the installation and also to verify durability. If we have uncontrolled air leaks, we penalize ourselves in not only energy efficiency, but we may have air leakage that could result in condensation, which results in moisture, which results in headaches that none of us want. So therefore, look at the blower door test and the test for air tightness, not just one for performance, but also one for quality control as well as durability. A SIP house can very easily achieve high levels of air tightness. In fact, having built a number of passive houses myself, I can attest to the fact that a SIP envelope, when properly installed and sealed, can quite easily achieve the standard of 0.6 air changes at 50 pascals of pressure when a HERS rater puts it in through a full blower door test. As this slide very poignantly points out, more than 40% of a home's total envelope loss is due to infiltration. That's air infiltration. That's air leaks, air leaking into and out of the structure uncontrolled. Not through your ventilation system, but uncontrolled leaks that are leaking through joints and cracks that weren't properly sealed. The control of those joints and cracks is what accounts for up to 40%, or in some cases more than 40% of the total loss of energy in the home's envelope. That's incredibly important. SIPs have fewer gaps, especially when we use larger panels with good design, and with the use of a surface spline, we have the ability to put in joints that are easy to make airtight. So you can then achieve better indoor air quality, better energy performance overall, if we maintain that air tightness that SIPs easily provide. SIPs are ENERGY STAR compliant. They are in fact recognized by ENERGY STAR, and if you read the small print, they'll even tell you you don't actually have to do a blower door test, because the folks at the ENERGY STAR program, having tested enough SIP houses, recognize the fact that they always pass the blower door test. I, however, would encourage you not to read that small print and say, gee, I can get away with not doing a blower door test. I would go back to what I said before, which is do a blower door test on every single house, and do it not just for verifying its performance, but just as importantly, verifying quality control as well as durability of the house. The rater, or the HERS rater, who does the blower door test on structures, will provide a score for the structure, and this score uses the HERS index. The HERS index is basically like golf. The lower the score, the better you're doing. A 0 score means that you are zero energy or net zero compliant. It means that you make as much energy as you use. In a modern day house, this means you must have some type of energy producing equipment. There must be some type of photovoltaic or wind or water energy producing equipment that allows you to get to that point. About as low as you can get without any of this equipment would be a HERS score of about 30 to 35. Somewhere in that range is about as low as you can possibly go without producing your own equipment. It's very tough to get that low. A standard new house being built to the code minimum standard will score a 100. So everything below that is an improvement, but beyond the model energy code. ResNet are the people, or the Residential Energy Services Network, are the folks that certify HERS raters, or referred to just as raters. And these raters will do the blower door test and then do the calculations using REM rate software to determine how well the house will perform. This can be done pre-construction. It can be done mid-construction when they do their first blower door test, which is when the first blower door test should be done so that we can make corrections in the envelope before the finishes are applied. And then ultimately the rater typically would come in and do a final inspection at close of or at certificate of occupancy to verify that everybody has done what they're supposed to do and we still have a good tight envelope. Continue with characteristics of SIPs. Let's talk about SIP R values. If we look at this chart, you'll see that EPS, or expanded polystyrene, in a 4.5-inch panel has an R value of about 14.4, whereas the XPS is about 19.5 and the polyurethane is 21.7. The confusing part about this is that if we look at the bottom, you'll see that our values are based on a mean temperature of 75 degrees. This is what the Federal Trade Commission requires us to market products at when they are insulation. So therefore, all products are rated at 75 degrees. The interesting thing about most foams is as the temperature drops, the R value actually increases. They have an increased resistance to the flow of thermal energy when the temperature differential is increased, i.e. the outside temperature drops more and more. So this is why you will see R values in some cases much different than you see on these charts, because the manufacturers are looking at one whole wall R values, which we talked before, or the fact that you actually get an improved performance when we start looking at cold climates. R values don't tell the whole story. You really need to consider air tightness as a part of the package as well. But this chart will show you that you can get R values very high, all the way up 45.9, 58.3, and that's just when you're looking at 75 degrees Fahrenheit, which is about the one temperature I can think of where we actually don't need insulation, but that's how we have to market insulating materials. When you're designing with any of the green building programs, the use of SIPS can benefit you greatly. Whether it be LEED, NAHB Green Building Program, Earthcraft, or any of the others, many of the attributes of SIPS will benefit you in your application for these programs. They're going to cut down on job site waste. The lower HERS index score will allow for a greater amount of points in many cases. Also, you get a lot of resource efficiency for using engineered wood products, and some of the recyclability aspects of SIPS, as well as low VOC requirements. There's a number of attributes of SIPS that will help you in the point race, if you will. Specifically, if we look at LEED v4 for homes, you're going to see that we have a number of points for both annual energy use, a number of opportunities in materials and resource, and down in environmental quality, where we talk about low emitting products. Again, that's the low VOC, provides a number of points as you move forward. If we look at the life cycle analysis of SIPS, we see a number of benefits. When comparing ourselves to traditional stick frame homes, the amount of energy invested versus that which is saved is about 10 times the amount. So we see a huge gain in energy efficiency over years, and this provides, of course, a reduction in global warming potential with the equivalent CO2 emissions produced, as well as we see the energy payback period in somewhere in the neighborhood of 5.1 years. Now this changes depending upon where in the country you're looking at. As we are in southern climates, it's shorter, or excuse me, it's a longer time frame for payback. If we go into the colder climates, the payback is much quicker, because of course the energy savings in the colder climates means that we can get a payback much quicker. And of course, recapturing greenhouse gas emissions, that occurs within 3.8 years. That emissions which are used during the production of those panels is then saved after 3.8 years because of the reduction in energy usage due to the efficiency of the SIP envelope. Within the residential energy code compliance, with the number of states having adopted 2012 already and now a number taking on 2015, we have to look at the model energy code or compliance with the energy code. Most people, the absolute most people, are only familiar with code compliance as it relates to the prescriptive method, meaning that they know that the walls have to be RX and the roof has to be RY, whether that be a 19, 22, or 24 in the walls, or a 30, 34, or 38 in the roof. It's the prescriptive method. It's just a line in the sand that says you need to be this high in R value in order to comply. But as I said before, R value is only half the picture. It's only half the story. The air tightness of a SIP envelope is why you will be much better off to use either the alternative method or the substitution method, or perhaps the performance method is the most advantageous in that it takes into consideration air tightness much more so than the others. And of course, prescriptive method doesn't consider it at all. It just looks at R value. So thinking about how we are in compliance with code is a whole lot more than just looking at a number on a page that says R value. Looking at the performance of the overall system is a great way to become compliant with the code, and in some cases having an R value that might not even have met it in the prescriptive method of compliance. The SIPs have a phenomenal way of complying with the code in a number of ways, and using the performance method is the best bang for your buck when calculating. Designers who are working on SIP projects will find it very useful to use the various load table charts and engineering charts that are a result of the testing that is performed by the certified labs discussed earlier. These tables, whether they be a table produced by an individual SIP manufacturer or the code report that is held by the Structural Insulated Panel Association, any of these tables can be used to determine various capacities and capabilities of the SIP, whether it be a gravity load, a transverse load, what the axial carrying capacity of a wall is. These load design charts are a tool that designers will use to verify their understanding or their capability of use of the various panels and various orientations within the project. Within SIP designs, we have to concern ourselves with the structural nature of the panels, and the structural nature of the panels are confirmed by laboratory testing or code approval based on the testing that is done by the individual manufacturers using certified labs. These labs result in evaluation reports. These evaluation reports provide all of the information that is necessary to show compliance with those various codes. They are available by the manufacturer that you work with. They can pass this information on to you to show full code compliance. Various SIP applications, not the least of which is SIP walls and roof. In the pictures here you can see in the one picture we have SIP walls with a truss roof, which we talked about in details earlier in the presentation. On the right side you can also see where we're dealing with SIPs over timber frames. It's not uncommon to use SIPs over insulated concrete forms, and of course hybrid construction of any kind is one where we can mix and match the use of SIPs and conventional framing or other types of energy efficient construction. SIPs is not a you got to use them all or none. It's a use it where it makes sense. If it makes sense on the walls only, use them on the walls. If it makes sense on the roof only, use them on the roof only. You have the ability to use SIPs where they make the most sense, whether that be on just walls or just roof. In some cases, SIPs can be used in a renovation scenario where the SIPs are creating a new roof or an overlay or something that provides an upgrade to the energy efficiency of an existing house. You should talk with manufacturers to see where this best can be applied for the situation that you're dealing with. The project that you're looking at right now is an 1872 historic preservation where SIP roof and walls were applied after the house was raised and put on a new foundation. The HERS score of this house, by the way, was a 47, so they really knocked it out of the park in terms of energy efficiency on this project in Ohio. The affordability market of SIPs is one that's been growing tremendously, and that's because it's clearly understood that the true cost of home ownership is not just principal, interest, taxes, and insurance, but it also includes utilities. And if you can take a project like a Habitat for Humanity project where the utility cost can be reduced substantially because it's so much more energy efficient, this means that SIPs actually become perhaps out of the box a more affordable way to live because you're not dealing with a large utility bill. These Chicago workforce housing projects utilize SIPs in a very simplistic design, but the end result was one that provided extreme energy efficiency and exceedingly low utility costs. If we want to talk about disaster resistant, These projects were part of the Make It Right Foundation after Hurricane Katrina down in New Orleans, and these projects were all made out of SIPS, again dealing with extreme engineering or climatic conditions. So you've got high wind speeds, you've got great deals of exposure. In this case, the SIPS allowed us to meet the engineering requirements of the project in an area where it's very, very important in order to be able to build right on the coast. This slide shows some modern or sustainable designs, those that might be considered not traditional. One in Washington, one in Michigan. Wherever you have a large flat roof or a modern design, the SIP panel can often meet the design requirements that you might have in those particular scenarios. SIPS actually had a huge resurgence in the timber framing community when timber framers recognized that a structural insulated panel was the ideal envelope to a timber frame. Here's a couple of projects that you can see on the screen. These projects enjoy the wrap of a structural insulated panel, which provides not only additional strength to the timber frame, which increases its racking resistance, but also gives it the modern day energy efficiency that timber frames of many, many years ago never seemed to enjoy. When we talk about engineering possibilities with SIPS, we have to very clearly understand the strength of the panels and how they can be used in order to maintain the strength necessary to meet the climatic conditions or those forces that are being applied to it. The project you see on the right even has the benefit of using SIPS that have been pressed in a radius, which means we now have a curved roof that is a continuous, fully insulated roof element that goes over top of the beams or the structures that make up the supporting elements. These slides show some very traditional craftsman style designs both in Minnesota and Washington. These projects were completely wrapped in SIPS, walls and roof. It gives you a very traditional look. From the curb you would never know it was built out of SIPS, but after you lived in it for a while and opened up the utility bill, you would not be surprised at all to know that it was manufactured or that it was built from structural insulated panels. One of the key elements of good SIP design is the support or the structural support of the roof. I can look at this picture and tell you that the panels span from eave to ridge. There's a ridge beam as well as a midspan beam, which might be referred to as a purlin beam on either side of the roof. This purlin beam breaks up that long span from eave to ridge, in essence putting the panel in a multi-span condition and allowing the panel to bear in multiple locations, which means that the panel, one, may not have to be as thick because it doesn't have to span as far, or two, does not need to put any dimensional lumber at the spline joints to supplement its capacity to span. So again, we go back to that surface spline joint connection, which allows for a improved energy efficiency by eliminating any thermal bridges in that roof panel. If we look at these panels, we can see that the panels actually have the ability to span some fairly long distances. Both of these cases, the panel spans from eave to ridge, which means it's in a simple span condition. Based on the area that we're building, the snow load or the total load, one has to determine what thickness of panel best meets the requirements or the loading such that the panel will do all the work. In SIP application, air sealing and header-free windows are key elements. This picture shows very clearly panels are being tilted up by hand. This is a nice thick wall panel. From the picture, I would speculate that it's a 9 1/4 core or a 10.5 inch overall thickness panel. You'll notice that the panel to the right has a window cut out in the middle of the panel. There is no header. The foam has been relieved to allow for the dimensional lumber to be recessed into that window opening. And in the bottom, or actually in 3 places along the panel that's being tilted up, you can see that the sealant goes around 3 different wire chases. So there's 3 various wire chases that run horizontally through that wall panel. All the panels are labeled. These panels were cut in the factory and sent to the job site, prefabricated, so that installation can be done very, very quickly. As a designer, you should not be concerned about the format of a SIP panel dictating how you design your project. If you have a complex design, let the design flow, let it be whatever it is that you want to design. Let the manufacturer and their reps work with you to coordinate the transfer of your information in whatever format you draw into the panel layout drawing that the manufacturers create, that ultimately allows the panels to be fabricated and shipped to the project, such when it all fits together, it creates the design that you have created before ground is even broken. So in summary of this course, that we've spent an hour together talking about structural insulated panels, one would hope that you can be able to describe and define what is a SIP and how it can be used in various applications, understanding what the energy strategies are when working with SIPs, as well as be able to illustrate the design and engineering methodologies that are used with structural insulated panels, and of course list and describe the current industry assembly standards, of which we only touched on a few. There's many more, and all of those are available through the information that are available to you directly from the manufacturer that you're dealing with, or with the Structural Insulated Panel Association. So we have the next 10 minutes for you to ask me questions. It's going to be a little bit difficult to do, but I would suggest that if you do have any questions, that you first and foremost contact the Structural Insulated Panel Association. They may or may not pass your question on to me. Again, my name is Al Cobb, and I'm with the SIPS School. I hope you've enjoyed this continuing education course. I've enjoyed narrating it for you, and hopefully we can do it again with another one real soon. Have a great day.